Good morning, everybody. Thanks for coming. So Holly and I, we work on the Windows Defender and Windows Defender Advanced Threat Protection research team. We're both data scientists, passionate about data and security, and we're quite excited to give you some insights and behind-the-scenes look at how we wrangle data, how we use machine learning to protect Windows Defender ATP customers from malware and advanced threats. So Microsoft, being a large organization with a variety of products and service offerings, it's sometimes a little bit difficult to make sense on where certain products fit in. So Windows Defender ATP is an endpoint protection solution, enterprise endpoint protection solution that integrates with Office 365 and ATA. So if we think about the endpoint, there's two primary attack vectors on how an endpoint can get attacked. There's email, and then there's web. So if we think about email, that is covered by our colleagues on the Office 365 ATP team that basically prevent malicious emails from getting delivered. If we're thinking about web and all the malicious activity along the kill chain thereafter, that is covered by the Windows Defender ATP solution. Now, all the way on the right, we have another product called ATA, which stands for Advanced Threat Analytics. And that is an on-prem solution that analyzes network data, primarily looking at user authentication, authorization, and information gathering signals to identify malicious user behavior, such as lateral movement. Now, when we let's deep dive into Windows Defender ATP a little bit more. So there's four aspects to the solution. There's the prevention, the protection, the post-breach detection, and the response. Now, our group sits within the Windows group, and that empowers us to change the operating system. It empowers us to make the operating more secure. And then also it allows us to instrument the operating system to give us signals to better protect, detect, and respond to the threats that we're seeing. And all the data that we collect from the endpoint, we combine with data from the intelligent security graph, and I'll talk about that in a couple of slides. And that gives us really unprecedented capabilities to detect threats. Now, before I talk about the particular graph, let me dive into details what stands behind these four icons. So on the prevention side, and what I'm going to talk about is not comprehensive. It's kind of some recent additions and creators fall update. We are having a variety of features, exploit guard, for instance. That is an umbrella term for a variety of technologies. So there's exploit prevention, where we're basically blocking certain actions taken by exploits in order to be successful. An example there being access to the export address table to kind of figure out the memory layout. Attack surface reduction is another feature of exploit guard, in which we can define policies to prevent exploits from succeeding. So an example there being, we can, for instance, prevent PowerShell from launching from a Windows word process, which we often see in an exploit or social engineering setting involving Word. And there's a variety of more features that are part of exploit guards. There was actually a session earlier this week, and if you want to learn more, I refer you to that session. Then we have App Guard, which basically isolates applications, and then Device Guard, that basically locks down the operating system such that only trusted applications can run. So that's kind of what stands behind the prevention icon. On the protection side, we also have a broad stack. Starts with web protection, aka Smart Screen. Here we're protecting users from malicious URLs, both on the social engineering and the exploit side. We protect users from phishing websites, as well as tech scam websites. This technology then is combined with application reputation, where we have models in place that basically assess whether a downloaded application is a known good application and show you a big scary warning if it's not. And then, of course, we have Next-Gen AV, which combines client and cloud protections covering a broad range of file types and fileless attacks with custom enterprise protection. So the prevention and the protection side is our pre-breach components to the solution, and we also have a post-breach solution, post-breach components to the solution, assuming that a threat actually is able to break through those defenses and end up on an enterprise network. So there, what we're doing is we're collecting generic behavioral telemetry and build models and heuristics on top of that. With all the alerts that we raise, we also provide context to the alert from our threat intelligence team that tell you who is behind an attack. So SecOps can basically utilize that information to assess the severity of the breach and take appropriate action. Now, on the response side, in Creators Update, we introduced some manual response features for the SecOps team, so they can isolate machines, they can blacklist files, kill processes. Now, with the acquisition of Hexadite, our product has automated response capabilities. And again, there was a session on Hexadite, I believe, yesterday that I refer you if you want to learn more. Now, all of this is exposed in a single pane of glass in form of an operations and analytics dashboard for management and reporting purposes. So I hope that kind of provides you an overview of what the Windows Defender ATP product is about. Now, this presentation is about talking about machine learning models, how we use machine learning to protect customers. And within each of these components, we utilize machine learning, and we'll give you some examples here in a bit. Now, data science and machine learning is really pivotal to Microsoft. There's a variety of teams that are dedicated to this space. So we have the Microsoft Core Data Science team. We have Microsoft Research AI. Then we have a variety of products in that space, an example being Azure ML, as well as Microsoft's Power BI, that enable customers to get insights into data and utilize this technology as well. Now, behind these products stand large-scale big data infrastructure and machine learning algorithms, and we as a product team participate in improving these solutions so we in turn can then utilize those and innovate in the protection and detection space. Now, when I talk to people about working at Microsoft to join us to protect customers against malware and advanced threats, I usually point to this as something that I'm personally very excited about, the Microsoft Intelligent Security Graph. At Microsoft, there is just a ton of data that we have available to make threat-relevant decisions. And the data is very broad. We have a lot of products and services, and then also very deep in terms of the scale. And that really allows data scientists to do amazing things and have Microsoft really lead in the cybersecurity space. So what is the Intelligent Security Graph? So it's a graph with a set of entities, and think of entities, things like machines, users, hosts, etc. And what we're able to do is aggregate information from a variety of products and services to these entities. So if we take an example, for instance, a host entity, we can get information about, hey, what does Bing know about it? Where does it rank in the ranking algorithm? When have we first seen this host? And we can look across, again, a variety of data sources. Has it appeared in email? Has it appeared in the search engine? Has anybody browsed to it? Those are the entities, and then we have relationships with other entities. So for instance, we can start asking the question, what file, what process has communicated with that host? And then we can further start asking now threat-relevant questions. Of the files that communicated with that host, which ones were malicious, were known malware? And then we can start moving into the belief propagation scheme, where we can kind of distribute beliefs throughout this graph, where basically the relationship, the fact that malware talked to a particular host, and the percentage here is very high, we can make inferences of that host being malicious as well. And all that data then becomes available for us to make threat-relevant decisions. And the breadth and the depth of this graph is just mind-boggling. I mean, you see here basically 4 main products: the Defender solution, our browser, search engine, and Office 365. And we're literally dealing with billions of entities. So that really gives us unprecedented visibility that I don't think anybody else has to protect customers from threats. Now, one of the downsides of utilizing data in such a way is that attackers also know that we're utilizing data, and they're trying to manipulate this graph and seeing whether they can trick our algorithms to make incorrect decisions. And when we go into examples later on in the presentation, I'll talk about this adversarial machine learning aspect a little bit more, and how we make our machine learning algorithms more robust against these sort of threats.
We wanted to walk you guys through a couple of basics around machine learning, how it applies to the security space, and a little bit about how we experiment on machine learning models and ship them to our customers. So first, what are some of the different applications of machine learning in the security space? There's 2 basic approaches. One is called supervised machine learning, where you take information from threat experts and use machine learning to exponentially increase your coverage or ability to detect. The second general type is unsupervised machine learning. I'll talk a little bit more about that in a second. There's pros and cons to each approach. For supervised learning, you have to start with threat expert rules. So the experts may label types of behaviors, they may label certain files, and from that expert information, machines can take over and exponentially improve your ability to detect those types of malicious activities. And I've got a couple of examples here that show sort of the difference between using an expert rule. So a threat expert may look at a set of malware files, and they may say, well, there's 4 basic aspects to this type of malware. I can create a custom rule that will detect this malware, but it's kind of coarse. It's a 4-sided algorithm that is a little bit imprecise. When you're talking about the types of signals that we see at Microsoft, the diversity in those signals can literally be hundreds of thousands of different parameters. That's huge. No one human mind can compute the perfect algorithm to use those signals and separate out malicious activity from benign. So what machines do is they take a couple of those labeled examples, and rather than creating a 4-sided box that describes a set of malware, it creates a more complex algorithm that's also more precise. So this is how we take supervised machine learning and exponentially increase what our threat researchers can produce. The second example is unsupervised learning. Now, threat researchers are fantastic, but like any human, they have biases. And these biases can lead to confirmation bias, where you have an opinion on what the truth is, and you simply use data to back up what you think that truth is, right? Machines can be lovely entities because they don't have this human bias. And with unsupervised machine learning, where you're letting the machines maybe cluster files in a new way that your humans haven't thought of yet, can help uncover new insights, new pockets of information that you may not have been able to discover on your own because of that human bias. So we have to caveat machine learning. Christian and I, we are practitioners in data science and machine learning. We love applying this concept to the security problem. But I have to caveat that machine learning is not a panacea to all security problems. Machine learning is a complement in a suite of protection technologies that is most efficient to help protect customers. So you can't do machine learning without threat experts, for example. You need your threat experts to help label files, to help train the machine learning algorithms to create the right output. So you can't do machine learning without the experts. The second piece of this is machine learning is not always the right solution to a problem. It may not be the most efficient solution to a problem. Sometimes those heuristics and those simple algorithms that the humans come up with are actually more performant on the client or can be used on the client to reduce the load that the client sees. So machine learning is really the icing on the cake. So you take these building blocks to help solve the simpler problems in a more efficient way, and then use machine learning for the prediction, for the hard problems, and for the facets that your humans can't see. Let's talk a little bit about some of the data and why this predictive ability is so critical when it comes to threats. When we look at threats that affect our customers, it's quite rare to see a threat affect more than one. So 96% of all the threats we see affect a single customer, and then they're gone. So we have a single chance to protect that patient zero. It's absolutely critical to have strong predictive abilities when you're talking about 96% of the threats you see. Even when you look at the distribution curve of the threats that do affect more than one person, you'll see in the little orange chart there, you only have a couple of hours before you get to the tail of that curve. So having this predictive ability is absolutely essential today to fight against today's threats. Here's an example of how we use machine learning in an overall process to ship out to our customers. So it starts with some categories of files or activity that is unlabeled. So we find it either through our unsupervised learning, from new clusters, maybe from samples that we have targeted, pull this into an automation process. And some of these samples can get auto-labeled and auto-categorized and feed into our labeled pool. Some of these don't get automatically categorized, then they may go to an experienced threat researcher to have a look at that file and put a new label on that file. Then it goes into the graph, where we combine all the signals from us, from the Defender side, with everything else in the intelligent security graph that creates all of the data that our machine learning models can use to process and create new algorithms to protect people. So from the graph, it's not just machine learning that is an output of all this data. Of course, we've got researchers who are also focused on heuristics and automation to create simpler, more efficient detections for customers. And these get shipped both to the client and also to the cloud. When it comes to unsupervised learning, there's a couple different facets that are super important when it comes to security. The first is unsupervised clustering algorithms. So these have the ability to take hundreds of thousands of features and come up with a completely different paradigm of finding new pockets of previously unknown files, malicious activities, that can help us discover the unknown unknown. So it can also help us discover files or related activity that may be unlabeled today, that we could then label to help better train our systems for the future. So two different benefits of the clustering is to find unknowns and then help build better labels for what we do know. Second way that we use unsupervised learning is through anomaly detection. So machines are really good at taking in lots of inputs and finding an algorithm to describe what is normal. And then we can use other algorithms to look for deviations outside of that norm and find when the pattern's not the same. Use that as a signal to investigate what's happening. So our basic method for getting models to production always starts out with an experiment. We've got an idea, a hypothesis, a different problem we're trying to solve. It might be a binary problem where we're simply trying to classify something as malicious or not, or maybe more complex, where we're trying to find similar files of a part of a malware family or specific classes of malicious activity. So it starts out with the problem definition. Then we go into initial feature selection. Typically, we work with threat experts to decide what features do you think might be useful for this particular problem that we're trying to solve. But of course, we'll also look outside of that box and incorporate other features that they may not have thought of that can also lend weight to the model. From there, we make sure we have a balanced label set. So this is incredibly important. So imagine you download a bunch of files from VirusTotal. You assume that they are all actually malicious, but you don't have a really strong clean set that you use to train your model. Or you've got a couple of clean files, but you don't actually know if that represents the real world, right? Without that balanced train set, your model may detect all of those malware files, but when you ship it, and you haven't done that balanced training set of having those clean files, it's not going to work in the real world. So this is critical to success of models. So we make sure we have a balanced set. If we don't, we work on upgrading the labeled set. We use threat experts. We also have what we call graders. And these are people who have some security training, may apply simple grades to, say, fish sites or different types of websites, different types of files, and without actually needing a threat expert to do that. So from labels, we'll create a couple of models. Often we'll try a couple different algorithms of models. We may tweak and tune the parameters. We may add features, remove features, do parameterization of features. So you can take an URL, for example, and take pieces of that URL and create features from that. So your feature is not the URL itself, but parameterized parts of that URL. Then we do our train and test. So you take your labeled set, split it into typically 80% for train, 20% for test. If all the metrics look good, then it's time to try it on some real-world data. We have a couple different methods of doing this. We can test our real-world data offline. We can also ship our models so that they are alert-only and not blocking. We can also incrementally release our models in flights. We use all or some of those options depending on the type of model that we're shipping. After we get that model into production, then we, of course, monitor the performance. We make sure the FP rate is where we need it to be, and we look for any kind of degradation that may indicate that the original parameters of the model are not continuing to perform. So we'll switch over to a couple of examples.
Yeah, so we'll talk about some specific examples, but first we'll look at one example across the entire protection and detection stack and how we utilize machine learning, and then we'll deep dive into specific problems within that detection stack and as we kind of jump around a little bit on the stack, we always give you a refresher on what component we're actually talking about before we dive into the specific machine learning problem. Okay, so the example here is basically an internet download example where the scenario is that the attacker is distributing emails with a malicious link where the user clicking that link would lead to a malware download. So right off the bat, we have Office 365 ATP that analyzes the properties of the email, the links embedded in the email, to prevent that email actually ever getting to your inbox. Now let's assume it does get into your inbox and the user is tricked into clicking the URL that points to a malicious download. We have Smart Screen that basically blocks that malicious download. There's a variety of expert rules and machine learning models behind a Smart Screen. Now, one thing that I want to point out here is that we're not learning that specific hosts are malicious through our models, but rather we're generalizing and learning characteristics on what makes a malicious host based on past behavior and observations. So for example, we could say, hey, if this host is with an infrastructure provider that accepts Bitcoin, the host is fairly new, and we're seeing spikes in traffic to that host. That could be an example of kind of the characteristics and that the model latches onto to determine that that host is malicious. Now let's assume the download succeeds. Basically, a file ends up on disk. Now Defender basically has the opportunity to inspect that file, extract static properties, emulate, and there's a variety of client as well as cloud-side models that then take advantage of the intelligent security graph to determine whether that file is malicious. Assuming that the file is not remediated, then Smart Screen's application reputation kicks in. It basically assesses, is this a known good file? So it's a positive reputation model. And if it's not a known good file, there's going to be a big scary warning. And that's actually quite effective in deterring users from executing that piece of malware. Now let's assume the user ignored the warning and the malware executes. Now Defender has the opportunity to inspect the behavior of that process and kill the process, again based on a variety of client and cloud-side models. Now assuming all this fails kind of in the pre-breach scenario, then we move into the post-breach scenario. Now we're monitoring generically what is happening on the machine, and there's a variety of models in place that basically are able to identify breach activity here. And if breach activity is identified, then that is getting passed on to our Hexadite component to automatically remediate the breach.
So we'll talk a little bit more about the two types of models that are in Smart Screen. There's two primary focuses. One is predicting malicious URLs, and the other is predicting file reputation. So for malicious URLs, we're looking for things that might indicate that the URL is a phish site, that it's downloading malware, serving exploits. This will help protect you from drive-by attacks, from phishing sites and text scams. The second component with application reputation, we're essentially building reputation on files that people are downloading, making sure that the application looks like a clean and good file. When we do not know whether the file is good and clean, it's first coming on to the internet, maybe it's not signed, looks a little suspicious. Smart Screen will send up a warning that says this file doesn't have a known reputation, and you can download that file, but it takes a couple of clicks and maneuvers to actually get to that file, and is very effective in ensuring that customers aren't downloading malware. These are both cloud services, so it's continuously updated on the cloud and nothing that you have to install or configure for the client. Thanks. So again, the 3 different categories for malicious URL prediction, deceptive ads, phishing, and malicious downloads and exploits. We've got around 100 mostly supervised models. These are generally linear models, very fast performant models. From a feature perspective, we look at parts of the URL. We look at time and traffic, domain reputation, IP reputation. We've got some offline models that actually use OCR, so we'll take a snapshot of the website. This is for some of our tech scam models, and we'll use OCR because you could scan that page, but often they're obfuscated, right? So if you actually take a picture of what is rendered to the customer and then use OCR to parse that, there's a lot of benefit that you can glean from using that information to help predict what is a malicious page. That's an offline model. So in general, we protect about 42 million people from malicious websites, about 8 million deceptive ads, and 3 million phish sites per month. Oh, what's happening? You want to know how this sounds? What this sounds like? It sounds like this. I'm going to wake you up this morning. Wah, 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 wah. Are you awake? This is a tech scam, all right? So I saw this just the other week, actually. You go to the site, and all of a sudden it looks like you're infected. There's a number that you're supposed to call. They say that they are Microsoft. I assure you this is not Microsoft. This is an example of what we strive to protect you against. Christian's going to talk about one of these models that detects these.
So Holly was talking about earlier that a lot of the smart screen models are based on infrastructure features, with the exception of the OCR model. But it's always good to kind of have a set of models that are orthogonal to each other. So a set of models that use infrastructure features and a set of models that use content features to really ensure that we have broad visibility and ability to protect you against this particular threat. So what we try to do here is build a content model that is able to identify text scams independent of the language used. Because obviously they're customize the language to their victims to increase the likelihood of the call and monetization. And so what we've resorted to is deep learning, in which we basically utilize screenshots in order to determine whether a page is text scam or not. And so what deep learning does, it really works well on unstructured data, such as visual data and auditory data. It basically automatically learns higher level concepts. So if you think about a screenshot, there's a set of pixels. If those pixels are next to each other, the learner is able to capture that and learn that that is a line. 2 lines in a 90-degree angle, it learns that that is a corner. A set of corners, colors, and curves, it could learn that as a Microsoft logo. And so we've been able to build a classifier on text scams. It works quite well in recognizing the overall page style. It's language independent and not subject to obfuscation, and really complements our infrastructure feature as well. Now, obviously, we're not taking screenshots of users' machines, so this is not a model that is deployed on the endpoint, but rather we're utilizing it currently on our backend to support our labeling efforts. Next, what I want to talk about is a little bit of adversarial machine learning. I alluded to this earlier during the presentation, where attackers are trying to poison the data that we work with in order to gain an advantage. So AppRep, as we talked about, is a component that basically assigns positive reputation to good files. In order to organically gain that reputation, that's very difficult. So for instance, one of the features that we utilize that has a strong indication of good reputation is prevalence. So if a lot of users are downloading a file and do that over a long period, we assign good reputation to that. That is very difficult to do for an attacker on the cheap. So what we've observed earlier this year is that there is an attacker out there that attempted to simulate downloads. And so they basically send us fake telemetry saying, hey, it's been downloaded from this machine, and that machine. So this was something that we were able to detect and prevent that file actually from gaining reputation, but it was a little bit of a warning shot across the bow. We wanted to make sure that our models generally are more resilient against these sort of attacks. So what we've done is build a device reputation model. Again, it's a supervised model that basically says, do we trust this machine to be a real machine? And then basically we utilize that information to filter out telemetry from non-reputable machines before we utilize it in downstream training sets. And some of the features that we use in the model are quite straightforward, like how many days have we seen that machine? Is the download behavior of that machine within normal parameters? Things like that. Now you may think that if we then use a model and carve out a lot of data that is utilized by our downstream models will affect those negatively. That is not the case. We just have a ton of data to work with, and if we carve out, say, 5%, it doesn't really affect our models adversely. Next, I want to deep dive into this particular model because it works just a little bit different from everything else that we talked about. And after the slide, you may think that I pulled some Jedi mind trick on you. Because basically so here's the problem. We're trying to assign positive reputation to these files that we're seeing users download. Now there are small publishers whose software is not very prevalent, and they're not investing into code signing certificates that allow us to potentially tie reputation to that signer certificate. So these are unsigned files, low prevalent. How do we build reputation on those files? So if it's a publisher that brings out various versions, what about if we group those files together into a bucket, and then basically that would potentially push those over our prevalence thresholds? So are we able to use machine learning to, first of all, tell us whether these files are similar? Now, similarity is a little bit tricky at the scale that we're dealing with at Microsoft, because similarity often requires pairwise comparisons, which is prohibitively expensive in the app rep space. So can we devise a model that A, tells us that files are similar, and B, do that in a way that we don't have to do pairwise comparisons? So what we've done is we built a model where the training set is structured in the following way. So the instances in the training set are similar files and different files, so two files. And the features are basically match properties of these files. So for instance, a feature could be, does the file size of file 1 and file 2 match? Now we want to make sure that we are creating a fuzzy hash, because if a publisher publishes versions of software, the file size actually will vary a little bit over time. So what we're doing is we're providing features to the learner with this fuzziness factor. So we can say file size match plus minus 1%, file size match plus minus 5%, and so on. And we basically let the learner, based on the data, decide how much wiggle room do we need to give to a property like file size before we consider a pair of files to be different. And so what that basically resulted into is the decision tree that you see on the right here, where it basically picked out all the properties that need to be met in order for a pair of files to be considered similar. And then we can convert that tree into a hash that essentially groups similar files together. So this is an example of where we don't really have a model that is running on a regular basis, but rather the learner is providing us with knowledge to derive the similarity hash that we can then later use to group files together.
We'll talk now about some of the models that are in Windows Defender antivirus. As we mentioned before, there are cloud and client-based models. I'll call out a couple of differences between the Windows Defender antivirus protection in comparison to Smart Screen. So Smart Screen protects on download, protects you when you're browsing to malicious websites. Windows Defender Antivirus, of course, has many more protection points. It will protect on download. It will protect when you plug a USB into your device, when you're grabbing something from a network drive. It will watch when you're executing something on your desktop. So there are many different protection points that Windows Defender covers that you would not get through Smart Screen. In addition to that, there are many different file types. So when we're talking about Smart Screen, you're mostly describing executables that you're downloading from the web. Windows Defender, of course, will look at content files. So it will ensure that you aren't opening up a macro document that has an exploit in it, or a Java file that's actually a malicious program. So there are many types of files that Windows Defender will cover that you didn't necessarily get in Smart Screen. And it doesn't only cover files, it also covers fileless attacks. So we monitor for malicious behaviors, process injection, and other things that can happen on your computer that don't necessarily include any type of file whatsoever. So we have client and cloud models. We primarily leverage our cloud models. We do have client models, but they're mostly to send up new signals and telemetry, and I'll talk about why we've made that decision here in a second when I cover the cloud models in a little more detail. So there's some great advantages to having cloud-based models. First of all, they are a lot harder to game. So you can imagine an attacker taking your client product, installing it on their network that is completely segregated from the internet, and testing every single variation of attack that they might possibly be able to produce until they find the one that evades your protection. If you've got a cloud-based protection model, they have to talk to you to get the answer. So they can't just test offline. They have to talk to your cloud. And if they are talking to our cloud, we can see their question. And this makes it, it's not impossible to game a cloud-based system, but it's much more difficult to game cloud-based models than local models. So for this reason, we rely on our client-based models to give us really loose signals about what's happening on the client, but not necessarily for blocking. The other benefit to having cloud-based models is that they don't require a lot of client compute power. Right? You build these heavy, intense, incredible models, use your cloud compute to do that. The client and the customer has no impact, right? They just get the answer. In addition to that, we can use all the contextual clues from the billion-plus signals that are in our security graph in the cloud. You can't push that down to the client. So a lot of good reasons to focus on cloud-based protection. We have both offline and inline models. Most of our models are inline, but we have some offline deep learning models that look for categorization of families and things like that. But most of them run inline and are pretty performant. We have different labeling strategies depending on what the model is doing. We've got some really aggressive models that are focused on first-seen files, so I'll talk about them in a bit, who have a more broad labeling strategy to have a more aggressive training set, essentially. And when we're looking at the feature set, it's hundreds of thousands of features that we include in these models. It represents over 20% of our customer protection today. That little graph shows you what the customer value's been month over month. So I'll talk about some of our block at first sight models. We've got one version that doesn't require a file, just works on telemetry alone, another that requires a file. So this first one, the primary goal of this model is to save patient zero. Save the first person who encounters the file, because we know that 96% of the malware out there, that's what it's going to do. So this model is uses an average perceptron model, and it does this incredibly complex set of this feature reduction to get to a very precise set that represents clean and malware files. This model trains very frequently. We've got some models that train a couple times a week. Some models We've trained once, and it's still working. This model trains a couple times a day because it is trying to keep up with the latest and greatest to make sure that it's blocking first-seen threats. When we shipped this model in our cloud telemetry, we were seeing about 0.5% of files that were first seen that turned out to be malware. When we shipped this one model, that increased threefold. So the benefit of this was huge. This is our main, this is one of the best O-Day finders at Microsoft today because it is great at classifying malware at first sight. The second model I want to talk about is also a cloud-based model, but it actually requests the file. The other model uses the telemetry that's sent up from the client. We don't need the file to make a blocking decision. The second model does. And this model, although in volume, is really minuscule in comparison to the other model that I talked about. It's super important because it's getting to those first seen files that we really don't have much information on yet. It asks for the file, runs a quick scan on it, and from that is able to make a very strong blocking decision. The other benefit of this model is that it brings in these super unique first-seen malware files as quickly as possible into Microsoft. And then from there, it becomes part of the graph, right? So that first-seen malware all of a sudden gets shared with all of our other protection systems. That results not only protection for that patient 0, but for anyone else who might encounter something similar to what that person experienced. Have you guys seen this slide already in any of the previous presentations? Okay, cool. So this is just a diagram of how that last model I talked about works. So when the client encounters something that is suspicious, sends a query to the cloud. From there, the cloud may deliver a response, but if the cloud, based on the telemetry alone, is unsure what the verdict is for that file, we'll ask for the file. We'll upload that file, and within seconds have a result from the scanner data and from the deep learning model that did the classification, and then send a block or allow response down to the client. This happens on an order of seconds. So there's a timeout, I think, of 20 seconds at the client. So this has to be super fast to make sure that we get a decision down. It's pretty rare for this to happen, like I said. Most of our blocks are happening from the first model that uses telemetry alone. But when we do encounter these files, it's super important for us to get it into the graph and get that customer protected. The other way we use machine learning on the Defender side is to look for anomalies. And now, rather than using this to detect new threats, we're actually using this to help communicate better with our customers. So sometimes when an outbreak happens, we'll have preventative detection for it. We'll get detection. There's a lot of ransomware that the fileless classifier is blocking today. But what that means is that sometimes it's difficult to see these surges of activity. And even though you, as a customer, may have been protected, if for some reason you're being targeted by some new surge in malware activity, you probably want to know what it is, right? Even if no one's infected. So this helps us spot those surges and create alerts and information, maybe get our threat researchers involved to go have a deep look at the threat. Even though we blocked it with the generic machine learning algorithm, we still need to know what it is. You still want to know why you're being targeted, what that would have done if it got in, right? That helps you build plans for preventative measures going forward. So I think as a company, from a technological standpoint, we have done a lot of work to keep our customers protected. We may not be as good at communicating that protection to you guys. So this is a feature that specifically helps us get information out to you faster.
So talking about the post-breach aspect of the solution, so assuming that a threat slipped through the cracks or the attacker was actually able to get on a network without malware at all, that's where our post-breach solution comes in. Give you some idea on the sort of telemetry that we collect from the endpoint that we then utilize in the cloud for these detections. It's a generic behavioral telemetry feed. So we get information about the processes that are created, the files that are created, network connections being made, registry modifications, and there's really no sort of aspect on the endpoint that tells us, report us this suspicious activity. It's again a generic telemetry feed, which is great because also that allows us to time travel. So let's assume I ship a new model or a new detection today. I can run that on telemetry from several days ago to assess whether something suspicious has going on that we missed back then. So let's talk about two models in more detail. One of them is PowerShell detection. So what we've seen as traditional defenses are becoming more powerful, attackers are moving to niche tools to gain control of the machine. Now that's PowerShell as well as other scripting languages. PowerShell is great for attackers in that it is a powerful language that is pre-installed, mostly used by developers and administrators, but again, it's turning into the tool of choice for attackers and pen testers. So can we use our client and our cloud to identify malicious scripts? So what we've done, we instrumented the AMC interface, which is the anti-malware scanning interface. That usually gets invoked by script engines for the antivirus solution to scan the script. We instrumented it in a way where basically now that script content is sent to the cloud in a script fashion. Here you actually see a couple of examples of malicious PowerShell script and benign PowerShell script. As you see, the malicious script is heavily obfuscated, and that's primarily to thwart any sort of signature-based scanning solution. All that is then sent to the cloud, and we extract features like engrams, certain API calls to essentially build a model to differentiate between these malicious and benign scripts. Next, I want to talk about process tree models. So here, one thing to keep in mind, in a breach scenario, malware can hide in the nooks and crannies of the operating system, such as malicious code running in the context of a legitimate system process. It also could be that the attacker was able to gain a foothold on the network without involving malware at all. And so we're really tasked with identifying whether a process is behaving in a malicious fashion. So what we've done is we're taking the general telemetry and building out process trees, as you see here in the middle, that basically capture parent-child relationships. So, Word, for instance, spanning SVC hosts, and then all the actions that are performed by these processes in the tree. Files are being created, network connections are being made, memory is being injected, things like that. And that is then the source of the data from which we extract features. So that could be, again, simple engrams, certain API calls, but also relationship features in the process trees that we know to be associated with malicious behavior, such as self-deletion or downloading and executing a file. That's something that we can basically make visible through this process tree. Now, one thing that we do as we build out these models, we're not building out one monolithic model that says, hey, we identified a bad process tree. Good luck figuring out where the malicious action actually is. But rather, we're building out separate models that focus on particular technology or topic areas. So we have a model, for instance, that merely looks at registry modifications. We have a model that merely looks at network communication. And then we combine the scores of these models in an ensemble to make a final decision. Now, why are we doing it this way? The reason being, as we are raising an alert, now we can actually point to specific areas that are responsible for this malicious classification. So we can say, okay, we see Word is suspicious behavior by Microsoft Word has been observed because we're seeing that it's making these sort of registry modifications. So that gives the SecOps much more context and the ability to investigate these sort of alerts. Now, generally, our ML models within the Windows Defender ATP solutions have a much greater precision than any sort of rules that are generated by our human expert. And then also for in terms of the volume that they contribute to the overall volume of Windows Defender ATP, they make up a significant chunk.
So we've got a couple of references here for you guys in case you want to dig into a little more information. There are a couple of key blog posts that are linked in the presentation and a white paper about machine learning in Windows Defender that you may be interested in. Links are here if you want to go have a look at those. There's also some additional sessions today and tomorrow. And if you missed some of the prior sessions about Windows Defender ATP earlier this week, you can go view those online if you'd like. So I think we've got some really unique opportunities at Microsoft. I think Christian and I, as data science practitioners and security practitioners, are super excited to be where we are at Microsoft with this wealth of data from all of these signals that we get from the graph, the focus of data science, machine learning, and AI at Microsoft. It's truly embedded in our culture. Not only do we have it embedded into each security team, but we have core teams at Microsoft whose focus is finding these cutting-edge technologies and algorithms that us as practitioners can apply. Couple that with the huge compute power of cloud that we've got at our disposal. It's a super exciting time to be at Microsoft to leverage all of these different technologies and experts within the company to deliver security to hundreds of millions of customers. So honestly, I hope you see the enthusiasm that we both have for this space. I hope you have learned a little bit about what we're doing in machine learning to protect our customers. We're happy to answer any questions you've got, either now or after the presentation, if you prefer. Thanks.
First of all, thanks for this really good presentation. Gave me some insights to better understand the product. I'm from Germany, so you might expect what my question will be. It's about data privacy and user behavior control. And if I remember correctly, with the fall creator update, you somehow press the user to first enable the cloud-based scanning and also to upload the sample files automatically. And I'm really concerned that you might upload intellectual property, e.g. a Word file which tells that we want to sell portions of the company and it's strictly confidential. So what do you do about that?
Yes, so those are PII file types.
Yeah.
And those are not, even when you opt in to automatically send potentially malicious samples to Microsoft, that part is not opted in. So the PII files, the customer sees an alert and they have to make a decision of whether they want to send that file or not. So
okay.
We've got some PII protection built into that so that people don't accidentally send things that they really didn't want to send.
So does it mean that I need to mark the document, or how do you detect that this is PII?
Well, any document we consider could be PII. Mm-hmm. So it's actually based on the file type and not...
Okay. So basically for every document you will ask the user, hey, is it okay to upload to the cloud? And if he's so stupid to say yes to a strictly confidential, then
yeah.
Okay.
They can make an educated decision about whether they want to or not.
Okay, thank you.
Where does Defender ATP get its data from? From the Defender client on Windows 10? So when you say running PowerShell, when you say registry changes, those kind of things, you're talking about ATP in the cloud, correct?
So we,
ATP Defend.
So we have a client called Sense that's baked into the operating system. It's independent of Defender that provides us with this generic telemetry feed that I talked about.
Okay.
As an enterprise onboards to Windows Defender, that sensor gets turned on through group policy.
Okay. Second question. The people doing Azure ATP Cloud and the people doing advanced threat analytics, two totally separate teams not working together whatsoever?
Separate teams working together.
Separate teams working together. Is Hexadite planned to come into ATA?
I don't know where they'll land.
I do not know the answer to that question, but the products are also integrated. So if you look at the Windows Defender ATP portal, there's integration points both to ATA and Office 365.
Okay.
Any other questions? Okay, thank you.
We've got one more.
I have a question. If we build a solution in Azure today using the PaaS components, and it's a solution that enables upload of file, stores in blob, and do things about it, will there be any solution for Microsoft that we can ship in files for scanning as part of that? So you can, because these solutions are based that you have a client, right? But if you're building a cloud solution which holds and processes files, and we also want to have scanning mechanism.
Scanning, I see. Is it an Azure-based system?
Yeah, yeah. So we're building using PaaS services like web apps and using blob stores and SQL, but we want to scan the file before because they are only processed in the cloud, and the customer uploads and downloads them. We don't want to be responsible for spreading malware.
I think it would happen automatically, but I would recommend talking to the Azure team here and confirming. Do you know offhand? Yeah.
But, yeah, okay.
Sorry. Any other questions? Okay. All right. Thanks, everybody.